All right, let's begin by defining probability using formulas, because ultimately formulas allow us to quantify the calculations so that we are able to base our decisions on numerical results. Now, here probability in terms of formula is defined as count of wanted items divided by count of all items. The item here is kind of left generic, and while that is good and all-encompassing and correct, it might be a little bit fuzzy, right? So let's make it a little bit more specific by giving a few examples. Items can be measurements. So we might say, we want to see, or we want to calculate the probability of encountering tall students. What's the chance of seeing tall students? So we need to set a litmus test. What do you mean by tall, right? Let's say 1.8 meters and above, they are considered tall. So now we start measuring the heights of students. One, then no, then two, and then no, and then three, and so on. Yeah. So suppose we encountered 4 students who are at various heights larger than 1.8 meter, taller than that. Out of 10 students, count of all items, yeah, all measurements. So then we will conclude that the probability of encountering tall students will be 4 out of 10, or 0.4. So that would be one way to apply the understanding of wanted items versus all items. Let's take a look at the Venn diagram on the right side here. So U represents the universal set, and that represents all our measurements. And events A and B are just subsets, and they declare those items that are interesting in the sense of A and interesting in the sense of B. And as I purposely put 2 balls here in between A and B, some events overlap each other. Yeah, so some events don't. Okay, so for example, A could be tall students. All right, B could be male students, and the 2 yellow balls represent 2 students who are both male and tall. Yeah, okay, so you can see that it applies to many cases, not just about students and height and gender. So here we just generically look at the colors, and we might ask, what is the probability of A? All right, so for example, if I close my eyes and randomly put my hand into that Venn diagram box and really randomly select a ball, what's the chance that I pick a ball that is in A? Now you can answer that question, right? By using, again, don't go by intuition, go by definition. So we count the number of balls in A, 5, and we divide by count of all items in the universal set. That's always 10. Usually the denominator is easier to count. All right, so we do that. And here we have 5 out of 10. You can say it's 0.5. That makes sense, because if I randomly pick, it's like I don't always pick, the left side or the right side, but I move my hand around, and I just randomly pick one. That's a good chance that I pick a ball that is originally in A. Similarly, we ask what's P of B, and you say, well, that's 3. Yes, we do count the yellow balls because they are in B. Yeah, they are both in A and B, but are they in B? Yes. So you have to count them. So 3 divided by 10, and that's 0.3. So far, so good. But you can also answer a bit of bizarre questions using the basic formula. If you don't suddenly just throw away everything and start using your intuition to answer questions. So, what's the probability of the universal set? Okay, don't panic. Count of all wanted items. But the question wants all items. So it's not C of W, but C of U, right? The universal set. Well, we will just do it mechanically, robotically, according to the formula. 10 balls on top, and bottom is by definition 10 balls, right? C of U, count of U. So that's one. That makes sense. That makes sense. What's the chance that I pick a ball and the ball is inside U, the whole box here? And that's for sure always the case. Yeah. Okay. So you can also see that when we count C of W, the lowest it is we don't see anything, and that starts with 0. It will never be negative. So it is clear that probability of any W, no matter how you define it, all right, blue balls, yellow balls, green ball, doesn't matter how you define it, it will always be greater or equal to 0 for any subset W in U. So this is called is an element of U. Yeah, or some notations are kind of very convenient, so I use them, but you should not fear them or translate them. Just get used to it, and you will actually learn to enjoy it, and maybe you yourself will be writing it. So C I use as a function to count, just representing an instruction to you to start counting, pointing fingers and keeping your numbers. So count, right? And I encourage you to, at any time when the problem gets tough, think of probability as count over count. Is that okay? All right, count of interested items over count of all items. Why? Because we are intuitively able to, or better able to, visualize counting 1, 2, 3. We can see that there are 1 ball, 2 balls, 3 balls, 4 balls. You see, it's easy to visualize, easy to keep track of. I don't know, at least it works for me a lot. And when you just deal with probability as a 0.1, 0.4 as a real number between 0 to 1, all right, it is tough. Yeah, it doesn't quite make sense. It kind of brings us back to definition 3, where it becomes our intuition. Just try to feel the probability of picking a ball in A as 0.5. It's tough. What does that mean? Okay, so now we reverse back. 0.5, right? Is that what you mean? Okay, so that means that if there are 10 balls in U, there will be 5 balls in A, so that P of A is 0.5. It's the same if you tell me P of A, probability of A, right, is 0.32. I'll be wondering, how should I internalize that concept, right? So how do I think of that? Okay, wait. I will just multiply by 100 and imagine that you have 100 balls inside here, too many to draw, but it's very easy to visualize, right? That there'll be 100 balls in here, and somehow inside this circle A here, there are 32 balls exactly, right? So a decimal number, 0.32, is very hard to visualize, very hard to think. But if you think about count over count, it is way easier to understand. Let's try it out. We have seen this before, or it is easy to understand that what is the probability of the complement of A? That means what's the chance that I pick a ball and the ball is not A, not inside A? That means all these outside balls. All right. If you think about it as algebra, there's a standard theorem here, very very basic and simple, which says that probability of picking a ball outside of A prime, is 1 minus P of A. That means the probability of picking a ball inside A, but you use 1 minus it, you will get exactly the other one. So why is that the case? I mean, some of you can see through it, but I'm going to even rewind back and say, suppose we don't understand this. All right, let's use the counting idea and see if we can make sense out of it. P of A prime is just count of wanted items that are in A prime. All right, divided by C of U. So we can do that by counting the balls, but more generally, if the picture is not there, then we say that outside of A, right, that A prime is a set. Set is a little bit hard, but we're going to just worry about the counting. We're not worrying about the set definition. We just worry about the total number of items inside there. So isn't it true, if you think about it, that anything not in A must be in the outside of A, right? All right, outside of A. And so the total number of items in the outside of A, and that is called A prime, must be the total number of items in the whole universe minus the items in A, because you are either inside A or outside A. You cannot be in both, right? The ball cannot be in both. So if the ball is inside A, C of A will take care of it. Doesn't matter how many it is, 5, 10, 17, 20, doesn't matter. And the total number of counts in the U, the universal set, minus whatever is in A, divide by C of U, because that's the definition, right? But then we can see that it cancels out 1 minus C of A over C of U. But C of A over C of U, that's P of A by definition. See? So we are back to proving this theorem simply by using the concept of counting.